Okay, so let's have the third one, which is a piston cylinder device provides 8 kilojoules of work to an external device. So 2 kilograms of air are contained inside the cylinder. If the internal energy of the air increased by 2 kilojoules per kilogram during the process, the heat transfer is, so I think we're looking for Q, right? Okay, so we're looking for Q. So this is a piston cylinder device. So remember, when we're dealing with piston cylinder, this is a closed system. Therefore, mass cannot cross the boundary. Closed system. Okay, so we have, what are the givens? We have work, right? Piston provides 8 kilojoules of work. So we have 8 kilojoules. Okay. So remember that it says here provides. Okay. So it must be it must be positive. Otherwise, it should be negative if it does not provide. Okay. So we have positive here. And we have 2 kilograms of air. So we have mass, right? Mass is equal to 2 kilograms. Okay, 2 kilograms of air. And then we have, if the internal energy of the air increased by 2 kilojoules per kilogram. Okay, so internal energy, that is a change in U. Okay, change in U all over M, because 2 kilojoules, that is change in U, but we have all over kilogram. So that is change in U all over M. Okay, so that's 2 kilojoules per kilogram. So what do we do from here? So we are looking for the heat transfer, or the Q, of course. So to get delta U, okay, to get delta U, so we have to delta U all over M times mass. Okay, so this is just 2, okay, 2 kilojoules per kilogram times the mass of 2 kilograms. Yeah, 2 kilos. So as you can see, we can cancel out the kilogram, and then we'll have 4 kilojoules. And then, of course, Q is just equal to the change in internal energy, of course, plus the work done. Okay, so this is just 4 plus 8. And then the final answer is just 12 kilojoules. I think that's it. And let's have the next one. Okay, so let's have the fourth one, which is a solar collectors generate 1 kilowatt per square meter of thermal energy using the sun's energy. So a collector with an area of 1 square meter heats water. The water flow rate is 30 liters per minute. What is most nearly the temperature rise in the water? So the specific heat of water is 4,200 joules per kilogram Celsius. Okay, so we are looking for the temperature rise. Therefore, we already know that what we are looking for, or the problem requires us to find, is the delta T, or change in temperature. Okay, so let's write down the givens. First that we have, so this is a solar collector. So we can say that this is a solar panel or a solar cell that is designed to heat the water. Yeah, used for heating water. Okay, so what are the givens here? So the solar panel has let's call it C. Okay, so that is we have 1 kilowatt per square meter. Okay, so that's the given that we have. What else? And the area of the solar panel, let's just call it A, is equal to 1 square meter. Okay, so that's easy. So what else? We have water flow rate is 30 liter per minute. We also have the specific heat of water, and we are looking for temperature rise in the water. Okay, so we have V is equal to 30 liters per minute. However, this V, okay, the volume is, if this is only a volume, if the given is only 30 liters. However, we have per minute. So this will become a volume flow rate. So I'll be just adding here, I'll just change the symbol that we'll be using. So instead of V, it should be something like this. Okay, So should be, so this will become your volume flow rate. Okay? So volume flow rate is equal to 30 liters per minute. So remember this one, because again, this is not simply the volume, okay? Because we have a parameter of time. Uh, we have a parameter of time in the denominator. Now, CW of water, that is the specific heat of water that's already given in the problem, that's 4,200 joules per kilogram Celsius. Okay, now what should we do next? Okay, so we are required to find delta T, right? So maybe this should be in Celsius also, right? Because we have a given of specific heat of water in Celsius. Okay, so next. Okay, so for the solution here, what we can do again is by energy balancing again. So what will happen here? So of course, what happens here is the how do I explain this one? Is the power generated, of course, the power generated by the solar cell, okay, or the power available in the solar cell or solar panel, that is the Q or the heat that will be absorbed by the water. Okay? Only the power available in the solar panel. Okay? Absorbed by the water. Okay. So what is the next step here? Okay, so what is the power available in solar panel? Of course, that will just be equal to the power must be equal to Q, of course, right? So P is equal to Q. Okay, so don't be confused that P stands for power, okay, in this case, not the pressure. But what is the power available in the solar panel? So that is just C times A, right? Just 1 kilowatt per square meter, and the area is just 1 square meter. I think this just is just equal to 1 again, okay? So CA equal to Q, of course, that is MCWT, but the C that we have here is for water. So CW, delta T. Okay, so we have volume flow rate. So what is the next step? So we already have C and A, right? Okay, let me copy this one here because we'll be needing this one. Okay. So let me just make some available space here because it's too small. Okay, I think that's good. One more. Okay, there you go. Okay, so what do we do from here? So let's use the volume density again. So rho is equal to m over v. Okay, so why do I use this one? So since we don't have v, of course, we don't have volume, but we have volume flow rate. Okay, so to make the equation balance for the volume density, that's m over v. So I will make this a volume flow rate, but however, I should make the numerator also a mass flow rate to make it balance. Okay? Because I cannot simply add the volume flow rate there and not doing anything on the other parameters. So to make it balance, I have to make both of them a flow rate. Okay, so we'll be using the mass flow rate over the volume flow rate. Okay, So we'll be getting the volume density for that one. And then cross multiplying it, you'll have mass flow rate is just equal to the volume density times volume flow rate. Okay. So we already know this that the raw of water is 1 kilogram per liter, right? Now, what is a volume flow rate? So we have 30 liters per minute. Okay, so we have 30 liters per minute. Okay, times. However, since we are looking for power, right? No, we need to use power, right? So power is in terms of, or energy is in terms of joules, right? And joules is, no, sorry, the watts must be in seconds. So we need to convert this one into seconds. Okay, because power is joules per second. So I'll be converting this also into seconds. So we have here zero point 0.5 kilogram per second. Now we got the mass flow rate in. So therefore I should make this also a mass flow rate. So making this a Q, or the heat flow rate, and making this a mass flow rate to make it balance. Okay, I think that's good. So I think we can now substitute the values. Okay, so let's substitute the values. We have C and A, which are both 1. Okay, so 1 kilowatt per square meter, okay, times 1 square meter, all equal to, that is your CA, the mass flow rate, which is zero point 0.5 kilogram per second, times CW. Okay, so what is a CW? Ah, yeah, the specific of water is already given. So we have here 4,200. And what is the unit? We have joules per kilogram Celsius. And we have the change in T, which is the one that we are looking for. Okay, so let's check the units first again. So we cancel, the square meter will be cancelled. So we'll be left here with kilowatts, kilogram will be cancelled. And what else? Change in T is in Celsius, right? So we can cancel those. And we are left with joules per second. Now, joules per second is also watts, right? Joules per second is watts, but we have on the left side kilowatt. So, therefore, I should remove here the kilo. Okay. So, removing the kilo, I'll just replace it by 1,000, right? That is kilo. Kilo is also equal to 1 times 10 raised to 3. So, 1 times 10 raised to 3 times 1, it will become 1,000. Okay, so the left side will just be watts and the right side will also be watts. Now it's balanced. Okay, so solving for that, using your calculator, you should be getting 0.4762 change in Kelvin. Or we can also have change in T is equal to 4.762 change in Kelvin, since we are talking about change in temperature. Okay, so I think that's it. So we can have the next one.